Okay, so here's an example of implicit differentiation. We have x to the fifth plus y to the fifth equals 40xy. And so notice we have x and y on both sides of the equation. It would be difficult or impossible to just solve for y and get it in the form of y equals. So this is where we're going to use implicit differentiation. And so we're going to go through and we're going to take the derivative of both sides of the equation. So normally I just write that I'm going to take the derivative and I don't do it yet. If we do something to one side of the equation, we got to do it to the other side of the equation. And so we're just taking the derivative of both sides. So when we take the derivative of y, that's a function of x. And so we need to remember that we're using the chain rule there. So just take the derivative like you normally would, but tack on the dy dx with that piece. So looking at the left-hand side, taking the derivative of x to the fifth, that term doesn't have a y in it. So I'm just going to take the derivative like I normally would. So the derivative of x to the fifth is just 5x to the fourth. Plus the derivative of y to the fifth. So the derivative of y to the fifth, that does have a y in it. So I can think of that as f of x raised to the fifth power. So using the general power rule, I have 5y to the fourth, but I have to take the derivative of the inside. And so I'm just going to write that as dy dx equals. So looking at the derivative of the right-hand side, notice it's a product. And so we're going to need to use our product rule. Let's think of 40x as one of them and y as the other product. Okay. And so product rule says take the derivative of the first function. So derivative of 40x is just 40 times the second y plus the first 40x times the derivative of the second. So the derivative of y is 1, but y is a function of x, so I have to write dy dx. I don't need those brackets there technically. And so we want to define what dy dx is. So notice that there's two terms in here that has dy dx. And so we're going to want to get those to one side of the equation. And any term that does not have dy dx, we want to get it to the other side. So let's subtract 40x dy dx. And so I'm going to have still this 5y to the fourth dy dx minus this 40x dy dx equals, well, I have this 40y over here. And I wanted to get this term 5x to the fourth to the other side. So this would be minus 5x to the fourth on this side. And so now we can factor out dy dx. So dy dx all times 5y to the fourth minus 40x is equal to 40y minus 5x to the fourth. So if we divide both sides by what we have inside the parentheses, we would get dy dx by itself. And that was the whole thing that we wanted. I notice that things are going to be able to simplify. Notice that when I divide by this parentheses, let's pull out a 5. And notice over here, this 40y minus 5x to the fourth, I can also pull out a 5. So if I pull out a 5 from the right-hand side equation, I'm left with 8y minus x to the fourth all over. And if I pull 5 out of what I'm dividing by, I have 5 all times y to the fourth minus 8x. And so 5s can cancel. And we're left with dy dx equals 8y minus x to the fourth, that quantity all over the quantity y to the fourth minus 8x. So there's an example where the one side wasn't a constant, but you're still taking the derivative of both sides. You just gotta then get all the terms with dy dx on one side, all the terms without dy dx on the other side, and then solve. If you have more than one term with dy dx, then you're gonna have to factor it out of all the terms that have dy dx in it. Okay, so here's an example where we want to find the first and second derivative using implicit differentiation. And so let's first rewrite this as 4y to the 1/2 power equals x minus 5y. So wherever we see a y and we take a derivative with respect to y, we're going to just rewrite times dy dx, the derivative of the inside. And so when I take the derivative of this left-hand side, bring down my power, so 1/2 times 4, that's going to give me 2 of the inside y, subtract 1 from my exponent. So subtract 1 from 1/2, that's going to give me negative 1/2 times the derivative of the inside. So times dy dx equals, well, the derivative of x, there's no y there, so just derivative of x with respect to x is just 1, minus, now when I take the derivative of 5y, so that has a y in there, so derivative of 5y is just 5, and times the derivative of the inside dy dx. So I have two groupings that have dy dx in it. So I want everything that has dy dx in it to one side of my equation. And then I want to factor it out. I notice this left-hand side of my equation, I can rewrite that with bringing down y to the 1/2 power to the denominator to make that exponent positive. And so this is the same thing as 1 over 2 square roots of y, adding that 5 dy dx to both sides, and then pulling out from both of those terms dy dx is just equal to x. So I just pulled every term with dy dx to one side, pulled it out of both of those terms, and just rewrote the left-hand side a little bit differently so that didn't have a negative exponent or a rational exponent. And so now we can divide both sides by that bracket. So we get dy dx is equal to x.
Wait, why is it equal to x?
Oops, not x. It should be equal to 1. Thank you. I don't know why I put x.
And wouldn't it be 2 over the square root of y, not over?
Yep.
Not, okay.
Yep. Yeah, I was just bringing down that. That's not good. I was just bringing that down to the denominator, make that positive, and that 2, you're right, should be up in this numerator. And so I have 1 all divided by 2 square roots of y plus 5. Well, let's clean it up. I don't like fractions within fractions. We can get rid of that by multiplying 3 by the square root of y over the square root of y. So this gives me dy dx equals the square root of y all over 2 plus 5 square roots of y. Okay, I'm not sure if they went further and they got rid of your square roots of y there in the denominator by multiplying by the conjugate, but I don't want to do that right now. I want to find the second derivative. If I find the second derivative, I'm going to first rewrite this. And I'm going to have to use the quotient rule. So taking the second derivative. So whenever I take the derivative, with a y in it, I'm going to have to write dy dx next to it. So quotient rule, derivative of our numerator. So that gives me 1/2 y to the negative 1/2 times the derivative of the inside dy dx. All of that times our denominator, which is 2 plus, in that case, just times the denominator. I'm going to leave as 2 plus 5 square roots of y, minus my numerator. When I write my numerator, I'm going to leave it as square root of y, but times the derivative of my denominator. So derivative of 2 is 0, and the derivative of 5 to the 1/2 power. So bringing down my power, I would have 5/2 y to the negative 1/2. I just took the derivative with respect to y, so I have to write dy dx. All over my denominator squared. So 2 plus 5 square roots of y, quantity squared. Okay, so we want to clean this up. The other thing that we want to do is wherever we see dy dx, and I'm going to wait till the very end, wherever we see dy dx, where you need to go back in and replace it with dy dx is, which is this, which we found when we took the first derivative. So I'm going to make my exponents positive, and let's see, I'm doing that. So in my numerator, I have this 1/2 square roots of y. Actually, let's pull out. Notice in my numerator, I have dy dx in common. Let's pull that out. Oops. So if I pull out that factor of dy dx, which they have in common in the numerator, and I'll start rewriting. So this piece here, this 1/2 times y to the negative 1/2 is the same thing as 1/2 square roots of y. I have it times this 2 plus 5 square roots of y, minus, so I have this square root of y in here, times 5/2. And I can rewrite this y to the negative 1/2. I can bring it down to the denominator, make the exponent positive, and rewrite it as a radical. And that is all over our 2 plus 5 square roots of y, quantity squared. So this actually is going to start cleaning up nicely. So notice that we can distribute that 1/2 square roots of y inside here. So I still have my dy dx out front. All times, well, when I distribute 1/2 square roots of y to this 2, notice the 2's are going to cancel and you're just left with 1 square root of y. Plus, and when we distribute this 1/2 square roots of y to this 5 square roots of y, the square roots of y cancels and you're just left with 5/2. Minus, and so notice in here, we have a square root of y in the numerator, a square root of y in the denominator, so those cancel. And you're just left with 5/2. All over this 2 plus 5 square roots of y, quantity squared. So our 5/2 cancel. And so we're left with dy dx, which I'm going to rewrite in a minute, all times 1/square roots of y divided by 2 plus 5 square roots of y, quantity squared. Think of this as a fraction divided by a fraction. So we can invert multiply our denominator. So we have dy dx. So I have inverting my denominator, I have 2, let's see, no, we don't. We just have 1 in the numerator, all over square root of y times this 2 plus 5 square roots of y, quantity squared. Okay, now I'm ready to go back in, and wherever I have dy dx, which I factored out, I'm going to replace it with what dy dx was. And dy dx at the original beginning of the problem, well, halfway through, this was the square root of y all over 2 plus 5 square roots of y. And notice that's going to cancel with, and we can rewrite some of what we have in the denominator here. So we have 1 over square roots of y, all times 2 plus 5 square roots of y, quantity squared. So square roots of y cancel with one another. And now notice that we have a 2 plus 5 square roots of y times a 2 plus 5 square roots of y quantity cubed. And so we can rewrite that as 1 over the quantity of 2 plus 5 square roots of y to the third power, because we have the same base at our exponents. And so our second derivative is the following. So this, you had to recognize that when you find the second derivative, you need to go back in and replace what dy dx was with the first derivative. And then also see how much you need to clean this up